Hi friends, welcome to new video, new lecture. This is the lecture number 11 and in this lecture we will discuss about the on-chip variation. By any chance, if you heard about anything about OCV and on-chip variation, just have a surface level knowledge. So I will suggest you to just understand what I want to tell you and what I want to give you the content about the D-rate and on-chip variation. So actually, uh, on-chip variation is something that till now we generally discussed about something related to the timing constraint in general. Like till now we just calculate the setup time and hold time and another arrival time, required time, all of the things like all slacks and all those things actually in general. But we didn't consider about any constant, any better resistance which we cannot afford when we go for the actual chip fabrication. Actually, this topic forced the entire timing industry to discuss about that not only the general timing, but we should also discuss about something critical in timing. How the critical things happening that generally when we go for fabrication in foundry for any SoC or any chip or any design, we should discuss about the electrical characteristics of the transistors and interconnect. Why OCV exists? Like what are the sources of the OCV? We should discuss about that. There are three type of source can actually contributing in the OCV. That one is process inconsistence, temperature fluctuation and voltage variation, which we actually called, if you know by any chance, that this is a PVT variation. I think, I hope that you know PVT variation. You heard about this term several times, I think. So coming to that, how that PVT variation can happen, I try to give the example so that you can understand. What is that? That manufacturing inconsistence, the process inconsistence can happen manufacturing inconsistence, inconsistence across the wafer. So how that is happening? Suppose that optical proximity correction, because you know that when we go for the fabrication in the foundry, mostly we used or discussed about the photolithography and lighting process, etching, those things. So one of the things like optical proximity correction issue can cause the channel length or thickness of the oxide of the transistor to vary slightly from one region of the die to another region. How that is happening? Like suppose you have, this is the, suppose you have this much amount of die to fabricate. So you didn't know that every corner of the point is actually same fabrication parameter is going. So maybe this corner have getting less because of the inconsistence, fabrication inconsistence. This corner may be getting slightly different in the channel length, slightly different in the thickness of the oxide. Those things can happen. So this is actually the process variation. Okay, now coming to the temperature fluctuation. What is that? Temperature fluctuation, if I want to give one example to you, that localized heating, how it is happening. Suppose the block of the logic toggling heavily, like when you do the computation more fast, or when you do the very fast computation or heavy computation, that time obviously 0 to 1 transition or 1 to 0 transition will happen so much or frequent. So that's why the toggling can happen more frequently, so that part of the chip can create a hotspot and making those transistors slower usually than the transistor in a dormant of the any block nearby. So obviously the temperature fluctuation can happen. Similarly, voltage variation things is like that it can happen by the issue of IR drop and noise. How that? Suppose this is your power pad. In particular, I just assume that this is the one cell. This is another cell. Okay, this cell is nearby the power pads. So whatever the cell needs, suppose 1 volt, and because of nearity or near proximity, this cell will get the proper 1 voltage for operation. But because this cell is more distant, so because of that it will can, because of the IR drop and noise, power noise, it can get lesser amount of voltage, suppose 0.85 volt. So there will be there is a hampered in the power, there will be hampered in the voltage variation. And PVT variation can impact the timing and the power. So actually that impact the design in terms of delay and power. So now come to that how the OCV model in STA. Till now I think you understand there is a variation when you send your design to the foundry for fabrication. In every die there is a different type of corner is created when the fabrication is going in the foundry. Like suppose one block or one cluster is created as a slow corner. One cluster is actually act as a fast corner, and another, suppose this block is a normal one. So you didn't know about, you didn't sure about which block is perfectly timed out, or which block is working in which uh, timing path. So whenever you go to calculate your timing in the particular data path or design path, you didn't know about anything about timing it can impact. The better to take a delay factor in general, which you can, like, is a pessimistic view. So that's why I said that a fixed delay factor is applied to the delay of all the cells and net present in the design. All variation, it's not mean that, so it will, the whole timing requirement will not fail. The mainly either the increase or the decrease the delay. So we have to take care of that. Without running thousands of Monte Carlo simulation in every particular timing path, the STA tool we can consider a pessimistic view that can give a bigger idea or the bigger picture when you calculate about the timing or when you say about the timing. That is actually called the derating. So that is the how we model the STA into the OCV. Okay. Now come, as I said, that apply timing derate factor to speed up or slow down a specific path artificially to simulate the worst case scenario. There is a two type of derate factor can be there. One is a late derate and another is a early derate. So let's understand that what is the late derate and what is the early derate. So late derate is that derate is greater than 1. Okay, and it actually makes a path slower. It means it increases delay, and it is used to model worst case, or you can say slow silicon. And early derate, obviously the derate factor is less than 1, and it makes a path faster, and which is decrease the delay, and it is used to model worst case, or you can say fast silicon. Why we discussed those two things, late derate and early derate? Because we have to incorporate this derate factor into the timing calculation or timing expression, so that's why we have to understand. So now coming to the, after understanding late derate and early derate, we have to know how that derate factor we are multiplying into the particular timing constant expression mathematically. So for that we need to understand about the when setup time, what are the pessimism we are applying. So when we talking about the setup time, that we are worried about the data which will arrive too late. So the pessimism here we applied, we make the data path as slow as possible. If you remember this type of picture we discussed several times, there is a two flop which is connected synchronously, and in between there is a combinational cloud. So this is the data path we all know, and this is the capture path, or launch, this is the launch path, this is the capture path. Okay, so we make the data path as slow as possible and clock capture path as fast as possible. So the launch path data should multiplied by late derate. One example I can take 1.2 just for example, and capture path multiplied by early derate. Suppose the example is 0.8. Now coming to the hold, we worried about the data should arrive as fast. So here the pessimism we applied, the data path is as fast as possible, and clock capture path as slow as possible. And here the launch path with multiplied by early derate. Example suppose 0.9, and capture path is multiplied by late derate, suppose 1.3. So this is the whole thing, what are the pessimistic view we are applying in the setup and hold time constant. Now coming to the another good concept, which is a artificial pessimism we can say. Till now we are taking the pessimistic view only on the OCV part with the help of late derate and early derate. Now coming to the artificial pessimism is what? If you remember this picture, that there is a two flop which is connected synchronously, but if you carefully remembered that this path is getting the same clock path, this path is getting this clock path, and this path, this second flop, this second flop is coming the sharing the clock which is mentioned here at 2. So in this, when we are calculating the launch delay, capture delay, all that, and multiplied with the derate factor, we multiplied the same or the common clock path at the same instant of time. This is this common clock path at the same instant of time with the late delayed factor also and the early delayed factor also. So this is the artificial pessimistic way, and this is wrong. If the clock network share, that's why I say that if the clock network share the common physical wire or net, this is the artificial pessimistic view. The physical reality is a single wire cannot be both fast and slow at the same instant of time. And the solution is that the difference or the STA tool should calculate the difference between the early and late delay on the common segment and adds it back to the slack as a bonus. Because what we know that we are calculating the launch path delay and capture path delay, and then we try to focusing that the violation is happened or not, and because of the violation we have to calculate the slack. If we calculate properly, which is actually a CPPR formula, that CPPR is the latest arrival time at a common point minus the earliest arrival time at a common point. And this CPP value, if we add it to the slack, then we'll get the better slack value. Maybe they are the violation which we actually take, which we are observing, maybe that violation will gone after we add the CPP value. We have to understand that common path pessimism removal is important here, because I have to give the example in that way. Suppose you calculate the slack with a simple design which we know the OCV, which we actually calculating on the basis of OCV, and you are calculating another slack value which is OCV plus CPPR. There obviously this slack value will be considered with the proper CPP value, and you will get benefited by when you add the slack. These are the whole concept of OCV and how CPPR is the artificial pessimism which act as a buffer in case we have a violation in the slack. Now coming to the types of OCV, there is a three type of OCV we actually discussed about. One is the flat OCV, one is the advanced OCV, and another is a parametric OCV. The flat OCV is nothing, it is a simple thing that we generally fixed something percentage of direct to the entire chip. This type of things, like suppose we are, this is the delay, and this type of things, suppose we are discussing flat OCV, like we are adding some percentage of, suppose minus 9% to 8% of direct factor, and this axis have a number of inverter variation. Okay, so we add something in general into the entire chip, but the advanced OCV is we used a table based on logic depth and physical distance. We maintain here a lookup table. Okay, and parametric OCV is nowadays we are most talking about, which is actually we model the entire design or the timing path in a probabilistic way. We model the delay as a statistical way. We try to calculate the standard deviation, variation, and the mean. Okay, it is something we model delay. We try to model delay as a statistical way. Mu or sigma we try to calculate, and here I hope that you understand what is the concept of OCV. This is a lecture which I try to give you the flavor of how the OCV thinks and as a concept, as a theory. In the next lecture, with the 2-3 example, I try to give a understanding view how actually we calculate the slack, STA, arrival time, setup hold time in the with respect to OCV and CPPR. Thank you for listening this video with your patience. Thank you.